Hello everyone, welcome to this brief video that will be about inspecting quality of software, and we will take a look at Amun inspections. This video is supportive material to an article that is from series How to Beat Python's PIP. And if you are interested in that article or you want to dive into some details, some terms that I will use, feel free to read the article. I will post the link to it in the description down below. So, what we will focus on? We will focus on inspecting quality of Python applications. More specifically, we will run a Python application that is using TensorFlow. So it will be some kind of machine learning application. And what we will do, we will use functionalities that are offered by TensorFlow, so algorithms that are already implemented in TensorFlow, and our application can use, so we don't reinvent wheel. If we use TensorFlow, it's not just TensorFlow that is installed, but TensorFlow is our direct dependency. This direct dependency introduces other dependencies, so dependencies on transitive libraries that TensorFlow uses either directly or again indirectly. An example of such transitive dependency can be NumPy, or another example can be ABSLPy. These can be installed in different versions following version range specification that was created by maintainers of respective libraries. This Python stack or these Python libraries and a Python application runs inside some Python interpreter that can be in different versions and can be built using different compiler options. Besides Python code, our Python application can also call to some native dependencies, the dependencies that are offered by operating systems such as glibc or CUDA. So operating system provides us this environment. Operating system also provides some kernel modules. So if you want to communicate with GPU cards, then you have respective kernel module that handles this communication. And again, operating system can be configured in different way. And this all software runs on top of some hardware that again has different configuration options, so different CPUs that can be different CPU architectures, but also you can use some GPU cards and stuff like that. This all creates a stack, and any issue in this stack can cause that your application misbehaves, produces wrong errors, or simply does not build at all, so you receive build time errors if you are lucky enough. If you are not lucky enough, then you can get errors on runtime that occur very rarely, and especially with Python, that is dynamic programming language, you can end up in very bad situations with your software, but this applies in general. We built a service which is called Amun. I will talk about it briefly. And this service accepts a JSON, a specification, what Python application we want to run, what are the direct dependencies, what are the transitive dependencies, what Python interpreter should be used, what are the native dependencies, how to run this application, and also what hardware should be used in order to execute the application, but also how to build, what hardware should be used when building the application. As already mentioned, this service or this component is called Amun, and you can find it inside Amun API repository that sits in thoth-station organization on GitHub. This service is completely open source. You can download it, you can run it, you can deploy it into your cluster. It's written in Python, and it uses OpenShift as a platform, so you need to run an OpenShift cluster. It also uses Argo Workflows, and these workflows create steps that need to be executed in order to derive some observations on quality of software that is run. The repository structure is quite straightforward, so I will not talk about it in details. You can also follow instructions and brief introduction in the README file that is present inside the GitHub repository. There's also a scheme how this service works, but that's something I will show you in this demo. So let's say we have Amun deployed in our cluster and everything set up. Amun offers us few endpoints that you can use. Some of them are get, some of them are post. I think the most important or most interesting one for us in this demo is the inspect endpoint. And this inspect endpoint accepts the specification, how the software stack should look like, and what should be inspected for quality. So here you can see some example JSON that is available on this endpoint. So what we provide some base container image that should be used. As Amun is a cluster native application, it uses container images to build software that are subsequently pushed into OpenShift's container registry and used for testing the application. So the application is completely built in the cluster, and then it's also verified for runtime aspects of the software. So here we can see that we are using UBI 8, that is Universal Base Image in version 8, running Python 3.6, that's the interpreter used. Then there is some configuration options for batch size. I will talk about it in a second. Here you can see configuration for build or build time requirements. You can see how many CPUs, what CPU model, what CPU family should be used, but also memory requirements. If the application would require GPU or CUDA during the build time, it would be present there. Then there are other configuration options such as information about environment, variables that should be injected into the environment, files that should be present or injected into the container image that is run. Then some additional native dependencies that should be installed. In this example, it's Vim. Then we have information about the Python stack, so you can see requirements. These are requirements of our application, but you can see also requirements logged. So here you can state all the versions, all the libraries in all the versions, specific versions that should be installed in order to run your application. And then there are also Python packages, additional Python packages from PyPI. These are different from ones that are used by your application. And then you can see also runtime requirements, so requests for CPU, what CPU model, what CPU family should be used, and also memory requests for runtime environment. At the end, one of the last options is script that should be used. This can be a Python script, or it can be also a shell script that will be executed during the inspection run. What we will put here, we will put a code that will check specific parts of TensorFlow library. We handcrafted these so-called performance indicators, and these performance indicators really try to compute or try to run some computational heavy parts of machine learning libraries or Python interpreter in order to obtain information about performance. So you can find these performance indicators in the performance repository in thoth-station organization, and you can find different performance indicators for different libraries. We will use one from the TensorFlow directory. So here you can again see some description in the README file and what information these performance indicators produce. If you are interested in their implementation, feel free to go to this repository and read the source code. I've already prepared an request or post request to inspect endpoint. And this request is formed out of JSON that again uses some base image that is S2I enabled. S2I is source to image, meaning specific build process specific for OpenShift. I've configured other parts. I think the most relevant are these configuration options, that is packages that are tested. So here we are testing TensorFlow that is coming from AICOE index. It's this index, and this index holds builds that are produced by Red Hat's AICOE, and these builds of TensorFlow are optimized for AVX2 instruction set or optimized for CPUs that have AVX2 instruction set. So we use this index to install TensorFlow, but we will also use PyPI to get or to obtain libraries that are transitive dependencies of TensorFlow. We have pinned TensorFlow to some specific version. Then you can see requirements logged, and this section corresponds to pip file log, so it obeys the structure that is used by pip file log as used by pipenv. So here you can see all the transitive dependencies that are installed and that are used by TensorFlow either directly or indirectly. We should be able to see an entry for TensorFlow. Here you can see also digest, verify provenance, and integrity of these artifacts installed. And here you can see that we will run some performance indicator. More specifically, we will use a performance indicator that checks convolutional layers. Okay, so what we can do, we can hit the execute button, and this specification will be sent to Amun API, and Amun API will respond with some inspection ID, that is the identifier specific for the inspection that we've submitted. We can go to Argo's UI, and as you can see, a few seconds ago there was created an inspection that is checking quality of our software. So the very first step, there's created an image stream inside OpenShift cluster where the resulting container image will be pushed to. Then there is created a build config which states how to build the application. This build config is created out of the configuration that was, or out of the specification that was submitted to Amun API. And here we can see that a build is happening inside the cluster, and this step will take a while. So in the meantime, let's take a look at other workflows that have been already successful or unsuccessful. So here we have some failed inspection. In this case, there was created an image stream, build config, but the actual build failed. So we will take a look at this build that failed. Every time there is some step produced or step done, either successfully or not successfully inside the workflow, we aggregate information about the given step. So such information can be build logs. So we aggregate these build logs We'll shortly take a look at them. Then we can take a look at another inspection. So here you can see inspections of TensorFlow's CPU version that is available on PyPI, Red Hat specific TensorFlow builds, but also inspections of Intel specific Intel specific TensorFlow builds. And this inspection was successful. So here you can see our known steps. So an image stream was created, there was created build config, the build was successful in this case. We aggregated build log information, even though the build was successful. And here you can see jobs, the actual inspection jobs that were created. If you recall, we had a parameter on API that was called batch size, and in this case, we requested to run 20 jobs. So all these jobs eventually run in parallel, and they execute the same Python script. So in this case, it was convolutional performance indicator specific for convolution layers. So once all these 20 jobs finish, there's again performed job log aggregation. So we aggregate these logs for possible further analysis, or if a diagnosis is requested in case of failures or bugs. Here you can see these 20 jobs, and hopefully we should be able to jobs running for our submitted inspection if the build was successful. So no, the build is still running, so hopefully it will finish very soon. In the meantime, while the build is still happening, we can take a look at the failure. So we can remember our inspection ID, and we can go to console, where I will use a tool that is called AWS CLI. This CLI does not talk to AWS, but rather talks to Ceph. That is deployed inside OpenShift cluster and is used as object storage for storing results of inspections and also build logs, inspection logs, and so on. So here you can see a listing of inspections that we saw also in the Argo UI, and you can see our failed inspection here. So let's take a look at data that were aggregated for this inspection. We have information about build, and here you can see the actual specification. This specification is the specification that we posted to Amun API endpoint. So let's print it to console, and here you can see the whole specification with all the parameters. Just to tell you a small hint, if we take a look at TensorFlow, we provide the wrong digest, so it uses digest pool that is not correct, but I cannot find it in this case. Okay, anyway, so let's take a look at logs of the build, and I did something wrong. Log, and here you can see that the expected digest was full, but the downloaded artifact TensorFlow CPU from PyPI has a different digest. So the build process failed because these dependencies had wrong digest there. They were the integration was wrong, or in this case, I explicitly put wrong digest just to show you an error state and aggregation of these errors.
Here we can see our inspection. So our build finally succeeded, and the build log was aggregated. And now we have 3 inspection jobs running. There are just 3 because of cluster resources that are available. So as you can see, once the job finishes, there is immediately created a new one. So let's take a look at results of this inspection that we've just seen in the Argo UI. So let's list what's available for this inspection. And we can see, besides our already known build, where we aggregate log and the actual specification, we can also see results. So we saw that there were 3 inspection jobs that were in successful state. So we already have 3 results present on Ceph. So let's take a look at the first inspection job. In this case, we have information about hardware. That is the hardware used on a specific node where the inspection job was run. And we have also the actual result of inspection. So let's take a look at hardware information first. So let's bring it to console. And what we can see information about platform, architecture of processor, some additional information about architecture platform, but also different CPU flags specific for CPU type, then information about bits, about the manufacturer, about features that are available on the given CPU and stuff like that. This all aggregation is done as part of init container that aggregates information before the inspection job is actually run. And then we can go to results. So let's bring them to console, and results are in form of JSON. And they collect various statistics and various information from process control board, from the kernels, information about the process that was running the actual inspection script. And we have information about signals, about context switches that the given process received, and stuff like that. So all the information that are available from the kernel for the specific process. Then we have information about the inspection. So we used convolutional or performance indicator specific for convolutional layers for TensorFlow. Then there are some statistics as printed by inspection performance indicator, additional parameters such as data format, type, destination type used, and padding and stuff like that. There's also aggregated information about standard error and standard output, script SHA, so digests of the actual script that was run in order to obtain information, then runtime environment configuration that we submitted from Amun API, and information about operating system and other things that are aggregated as part of inspection jobs. So here you can see that our batch is still running, and once all of these inspection jobs finish, we aggregate also logs that are printed to containers, standard error, or standard output. So we capture also logging information or logged messages and things that. So here you can see how stuff is proceeding.
Just one thing to mention here in the article, I mentioned a component that is called the Dependency Monkey, and the job of the Dependency Monkey is to construct the application stack dynamically. So Dependency Monkey can pick which versions of which libraries should be introduced into the tested stack. So it's, let's say, smarter resolver, and it can say, for example, that some versions of Vercel should not be present or should not be resolved, and then respect the dependency graph following these rules that can be stated in Dependency Monkey rounds. I will talk about these in the upcoming section, the upcoming articles of how to beat PIPs, PIP series. That's it from me. So if you have any questions, feel free to reach out to us on GitHub or Twitter. Our Twitter handle is thoth-station. So thank you for your attention and see you next time.